Okay, this is a classic problem in circular motion, which is called conical pendulum. And generally what a conical pendulum is you have a mass hanging on a string and it's whirling about in a little circular orbit here. And generally what you're asked to do is calculate the period of the pendulum and the tension in the string. You're usually given these parameters like the length of the string, the angle to the vertical direction, and so we approach the problem like we would with any F equals ma problem. We draw the free body diagram on the pendulum bob. And the pendulum bob would have the tension force of the string upwards like this and gravity straight down. Those are the only two forces which are acting on the pendulum bob. So as we were talking about in this chapter, we want to resolve our force vectors along a direction towards the center of the circle, called the centripetal direction, and also a direction perpendicular to that, let's say the y direction. So in this case, if we were going to take a look at that coordinate system would be like this and like this, right? Our positive centripetal direction would be this way, and our positive perpendicular direction, or y direction in this case, would be this way. So we have to resolve this tension vector along both a centripetal and a y direction. So if we do that, realizing that this angle right here is our angle that we're making with the vertical, the component of the force in the centripetal direction would be the tension times the sine of the angle theta, positive because it's pointing towards the center, and the other component would be the tension cosine of the angle theta, and it's positive because it's pointing upward. And then the gravity vector is pointing in the negative y direction. Okay, the centripetal acceleration, since we want the period of the pendulum, the best one to use would be 4 pi squared r over t squared to make things the least amount of work. All right, well then we're just going to set up our F equals ma equations like we're used to doing. And we do one for the centripetal direction and one for the y direction. And as we get started, then we would have ft sine theta equals m 4 pi squared r over t squared, centripetal acceleration, right, AC. And in the other direction, we're not accelerating up or down, so the sum of these forces is just equal to 0. This gives us an expression for the force of the tension, which would be mg over cosine theta, which you could substitute back into the problem right over here. All right, so we'd like to solve for the period of the pendulum first. And doing so, and after making that substitution, now it becomes algebra. And just being very careful with what we're doing, we'd have mg sine theta over cosine theta, which can be re-expressed as the tangent theta. And then we'd have m 4 pi squared r over t squared. So rearranging, notice that mass cancels out from both sides of the equation. That leaves us with the expression for the square of the period after we do the algebra, 4 pi squared r over g tangent theta. Note that the r that we're going to put in the problem is the radius of the circle. And if we know the length of the string and we want to find the radius of the circle can be expressed as the length of the string sine of the angle theta. All right, because that just makes a triangle. All right, once we do that substitution, plug in our numbers, okay, and solve for the square of time, we get a period of 3.30 seconds. All right, so it's not whirling around very fast. It's a pretty long string. Once we have that expression, the next part of the problem asks us to find the tension. And actually, we could have done that probably first, because from the expression in the y direction, we just saw that we could solve, we had ft cosine theta was equal to mg. And substituting in for that, we end up with a force of 15.2 newtons. Again, that equation just came from our y column right here. Substitute in the mass, g, cosine of the angle theta, and that gives us the tension in the string, 15.2 newtons. And that's how you approach a conical pendulum problem.